Hello. So good afternoon, everyone. Uh, just wait. I'll first share the screen. Hello. So in last lecture, we have seen the boundary conditions, right? So boundary conditions means when we are considering the two different materials. Here we are considering two different dielectric materials having different permittivities. That is epsilon 1 and epsilon 2. And in between these two, there is a boundary. Now, we are finding here different components, that is the electric field intensity and electric flux density and their tangential and normal components we are finding there. So here for finding this E bar component, that is electric field intensity, we are considering one closed loop, that is A, B, C, D, A, and the total height is delta H. And for finding this D bar, we are considering one closed surface, that is one cylinder having total height delta H. Now, half part of both is placed in region 1, that is having permittivity epsilon 1, and the remaining half part is placed in region 2, having permittivity epsilon 2. Okay, so here up to yesterday's point, we obtained the equations for the E bar and we proved that this E tan 1 is equal to E tan 2. That is the tangential components of electric field intensity in both mediums. Okay, in both mediums, that is epsilon 1 and epsilon 2 are same. The tangential components are same here. Remember. Now we have to find here. After that, we have seen that this d tan 1 and d tan 2, right? The tangential components of the electric field intensity are same, but tangential components of electric flux density are related with this relative permittivity. That is d tan 1 divided by d tan 2 is equal to epsilon r1 divided by epsilon r2, right? So it is related by this. Okay. Now today we'll find here the normal components. Okay, normal components by using the Gauss law. So here we know, as we are considering there one cylinder that is placed on the boundary. One cylinder is placed on the boundary, right? So uh, and for that purpose we are finding the electric flux density components. Now uh, q is equal to close surface integral of d bar dot ds bar, and this is the Coulomb's law, right? The Coulomb's law is closed surface integral of d bar dot ds bar, and it is equal to q. It is equal to psi, or psi is equal to q. Now, this is the closed surface integral, and our surface is nothing but one cylinder, right? One cylinder, it is having a closed surface. Now, this cylinder is having the top surface, bottom surface, and these sides. Okay, all sides. So, this closed surface consists of top, bottom, and side. So, while taking this or while finding the charge, we have to consider all the three sides there. Okay, all the three sides. So this is closed surface integral of d bar dot ds bar is nothing but the integration of the top surface. Okay, integration of top surface of d bar dot ds bar plus integration of bottom surface of d bar dot ds bar and plus integration of side surface of d bar dot ds bar, and it is equal to q. Okay, so if we make this delta H is equal to 0 at boundary. Okay, so concentrate here. Now at this boundary, at the boundary. So at the boundary, what will be present when this delta H will be equal to 0? At the boundary, this total height is equal to 0. If total height is equal to 0, the side integration becomes 0 and only your top surface and bottom surface will be present there. Okay. So समझता है ना? Getting this or not? So at the boundary, when we take this delta H is equal to 0, means delta H will tend to 0 at the boundary. So only your top surface and bottom surfaces will be present there. Okay. So here, as delta H tends to 0, the side integration of this d bar dot ds bar is equal to 0. Therefore, integration for the top of d bar dot ds bar plus integration for bottom surface of d bar dot ds bar is equal to charge q. Okay, it is equal to charge q because only this top and bottom surfaces will be present at the boundary and this side surface is equal to 0 there. Okay, so now we have to find uh, uh, this d bar component. Okay, d bar component. So the mod of d bar is equal to dn1 for dielectric 1. Okay, this is one suffix is for medium 1 and this 2 suffix is for medium 2. Okay, now for medium 1 it is dn1 and for medium 2 it is dn2. Okay, or you can say as for dielectric 1 and for dielectric 2. Now therefore the integration for the top surface of d bar dot ds bar is equal to, now why we are taking here the tangential normal components, why we are taking here the normal surfaces and bottom surfaces. So uh, and uh, therefore we are considering this as the we are considering the normal components because these are perpendicular. Okay, from the boundary, both the surfaces. That's why we are considering the normal components here. Remember, therefore the integration of d bar dot ds bar for the top surface is equal to in region 1. This top surface is in the region 1, right? Top surface is in region 1. Therefore, it is equal to dn1 integration for the top surface of this ds bar. And this ds bar is nothing but delta s here, differential top surface we are considering as delta s. Okay. So it is equal to dn1 into delta s. Okay. Now for top surface, direction of dn is entering and for bottom, direction of dn is leaving the boundary. That is both are in opposite direction. Okay. Both are in opposite direction. So just see here. So when we are considering this top surface, actually at the boundary, this total H, when this total H tends to 0, that time this top and bottom surfaces will be at boundary. But this for this top surface, which is placed in region 1, is entering the boundary. Okay, the direction of dn1 is entering the boundary, but for this bottom surface, when this bottom surface is on this boundary, that time for this bottom surface, the direction of dn2 is leaving the boundary. Means it is in opposite direction of boundary. One is incoming there and other is outgoing there. Right. So uh, these are in opposite direction. Therefore, the sign for dn2 is considered negative there. Okay, so therefore integration for d bar dot ds bar of for the bottom surface is equal to minus dn2 integration of ds bar for the bottom surface, and it is equal to minus dn2 into delta s. Okay, now remember this d bar dot ds bar for the top surface, which is placed, this top surface is placed in region 1 or in dielectric medium 1, and the bottom surface is placed in dielectric medium 2, right? Therefore, for first one it is positive and second one is negative because the direction is opposite. Okay, therefore, and now we have to equate this equation, that is integration of the top surface of d bar dot ds bar plus integration of bottom surface of d bar dot ds bar is equal to charge q. Now for the top surface it is dn1 delta s, and for bottom surface it is minus dn2 delta s. Okay, and this is equal to charge q. This is equal to charge q, but this q is equal to rho s ds. We know that the charge q is also given by rho s ds, right? uh, uh, or rho s into delta s. So instead of this equation, this q is equal to, we can write this as rho s into delta s. Now delta s is taken common from the left hand side, and for right hand side it is also present, so we can write this as dn1 minus dn2 is equal to rho s. This delta s and delta s from both sides get cancelled here. Okay, now since here rho s is equal to q upon delta s, we have seen already these equations in second chapter. Now in perfect dielectrics there is no free charge available. Okay, so when we are considering perfect dielectric material means there no free charges are there. So if the free charges are there, these are the conductors, and dielectrics are those having all the bound charges. No free charges are there. Therefore, the charge density, the surface charge density is equal to 0 there. Yes, therefore, this dn1 is equal to dn2. Okay, means it is equal to 0 and dn1 is equal to dn2. Now we have to relate to this. Now, we are finding here the normal component, right? So from this normal component of this d, we have to find the normal component of e. Okay, in previous stage what we did in previous stage, we obtained there the we get there the tangential components of electric field intensity, right? That is e tan 1 is equal to e tan 2. Okay, from that we can find the tangential component of d. Okay, so here in this normal component, dn1 is equal to dn2. So from that we can find the en1 and en2. So we have to relate these. Now we know the relationship between d bar and e bar, right? So d bar is equal to epsilon e bar, right? D bar is equal to epsilon e bar. Therefore dn1 is equal to epsilon n1, and dn2 is equal to epsilon 2 into en2. Okay, so here dn1, to find this one component only. Okay, one component, we are taking the ratio here. So dn1 divided by dn2 is equal to epsilon 1 en1 divided by epsilon 2 en2. Okay, and it is equal to 1. It is equal to 1 as this dn1 is equal to dn2. Okay, so here we know that this epsilon 1 is nothing but, what is epsilon 1? Epsilon 1 is equal to epsilon 0 into epsilon 1 is equal to epsilon 0 into yes, anyone? Epsilon 1 is equal to epsilon 0 into Pradyumna, Mohini. Okay, so this epsilon 1 is equal to epsilon 0 into epsilon r1. Okay, epsilon 0 into epsilon r1, and epsilon 2 is equal to epsilon 0 into epsilon r2. Okay, this dn1 is equal to epsilon 1 into en1, and dn2 is epsilon 2 into en2. So here epsilon 0 and epsilon 0 from both get cancelled, and only the term remaining is epsilon r1 divided by epsilon r2. Now these two terms are equal now, right? That is dn1 is equal to epsilon 1 en1, and dn2 is equal to epsilon 2 en2. So this is equal to 1, and we have to find this en1 divided by en2. Now en1 divided by en2 is nothing but epsilon 2 divided by epsilon 1, and this epsilon 0 will get cancelled there. Therefore the remaining terms are only epsilon r2 divided by epsilon r1, and these are the relative permittivities of medium 2 and medium 1 respectively. Okay, so any doubt up to this point? समजले का सगळ्यांना? येस और नो? समजले का? Yes, anyone? Okay, so can anyone tell me what is the tangential component of e bar? Yes, e tan 1 is equal to what? Both are same or different? Remember, tangential components of electric field intensity are same. That is E tan 1 is equal to E tan 2. तुम्हाला हे समजलं की तुम्ही D component find करू शकता. Okay. E tan 1 is equal, and normal components of electric flux density are same. That is dn1 is equal to dn2. Okay. So remember these two. Then you can find their relations. Means if you know the tangential component of E, you can find the tangential component of D from the relation D bar is equal to epsilon E bar. And if you know the dn1 is equal to dn2, then you can find the normal component of E bar also. Okay, so you should first know the basic terms, and these boundary conditions are also asked as a MCQ question. Okay, MCQ क्वेश्चन मध्ये पण विचारतात आणि असा क्वेश्चन्स पण विचारतात, त्यामुळे प्रिपेअर करा. बाउंड्री कंडिशन्स आर इम्पॉर्टंट हियर. ओके, नाउ द नेक्स्ट पॉइंट इज refraction of d bar at the boundary, right? So we are considering two different dielectric materials having permittivities epsilon 1 and epsilon 2, right? So we have to here consider one boundary. Permittivity is different, that is epsilon 1, epsilon 2. Now this is d1, that is in boundary in region 1, and this is d2 in region 2. Okay, so these perpendicular components to the boundary are nothing but your normal components, and these are the tangential components. Okay, so from this only d bar, we are getting this normal component and tangential component. Now this is your tangential component, so this is also d tan 1, and this is normal or perpendicular. Uh, so parallel to this is also the dn1. Similarly, and this is making an angle theta 1. Similarly, you can find this theta 2, and the normal component of d in region 2 is dn2, and this is total d2 bar. Okay, and theta 2, they are making an angle of theta 2, and tangential component is this one. Okay, so we have to find now again the relation. So here, the relation between d bar and e bar is d1 bar is equal to epsilon 1 into e1 bar. Okay, and d1 mod of d1 bar is equal to d1, mod of d2 bar is equal to d2. Now we have to find here the dn1 and dn2. So from this refraction figure, dn1 and dn2. Okay, now we can tell me. So dn1 is the normal component, and this is the adjacent side of the uh, okay, of this diagonal. Therefore, just tell me what will be the cos theta. If you want to find the tangential component, you have to consider the sine, right? That is the front side. And if you want to find this normal component, you have to consider the adjacent side, right? So what is cos theta 1 here? Cos theta 1 from this triangle, what is cos theta 1? Yes, anyone, what is cos theta 1? Hello, what is cos theta 1? You don't know? No one knows about cos theta 1? Praveen, what is sin theta 1? Pratiksha, Renuka, yes. So the cos theta 1 is equal to dn1 divided by d1 bar. Okay. So here it is given cos theta 1 is equal to dn1 divided by d1. So from that you can find the normal component, that is dn1 is equal to d1 into cos theta 1. And similarly cos theta 2 is equal to, for the dielectric medium 2, this cos theta 2 is equal to dn2 divided by d2. Okay, dn2 divided by d2 means dn2 is equal to d2 cos theta 2. Okay. So, and we know from the boundary conditions that dn1 is equal to dn2. Therefore, dn1 is equal to d1 cos theta 1 is equal to d2 cos theta 2. So, and d tan 1 divided by d tan 2 is equal to epsilon 1 divided by epsilon 2. So, from this triangle, again, we can see that we can find the sine theta also. So this sine theta 1 is equal to the front side. Front side is the tangential side, right? So it is d tan 1 divided by 1, and sine theta 2 is equal to d tan 2 divided by d2. Okay. So this d tan 1 is equal to, here we are getting the tangential component. So the d tan 1 is equal to d1 sine theta 1, and d tan 2 is equal to d2 sine theta 2. Okay, so therefore this d1 sine theta 1 divided by d2 sine theta 2 is equal to d tan 1. Okay, d tan 1 divided by d tan 2. These are nothing but the tangential components and the ratios only taken here. Okay, ratios only taken, and it is equal to epsilon 1 divided by epsilon 2. Okay, from this relation, uh, now tan theta 1. So tan theta 1 is equal to d tan 1 divided by dn1, and tan theta 2 is equal to d tan 2 divided by dn2. Okay, that is the tangential component. So this is tan theta is nothing but ratio of the sine and cos, right? Sine and cos. So for sine theta, we are getting this d tan 1. Okay, and for cos theta, you are getting the normal component, that is dn1. Therefore this tan theta 1 is equal to d tan 1, and this cos theta is that cos component is the dn1. Okay, so this tan theta 2 is d tan 2 divided by dn2 divided by dn2. Okay, so again, if you are taking the ratio, that is tan theta 1 divided by tan theta 2 is equal to d tan 1 divided by this dn1 divided by d tan 2 divided by dn2, means it becomes d tan 1 into this dn2 divided by d tan 2 into dn1. Okay, so and we know that this dn1 is equal to dn2. So if both are same, dn1 is equal to dn2, so their value will become 1. Uh, they get cancelled there, therefore it will become 1. Therefore this tan theta 1 divided by tan theta 2 is equal to only this term, that is d tan 1 divided by d tan 2. Now tan theta 1 divided by tan theta 2 is equal to epsilon 1 divided by epsilon 2 is equal to epsilon r1 divided by epsilon r2, and this is called the law of refraction. Okay, so here we are finding the different components. Okay, that is the tangential, then normal. Okay, now they are asking sometimes examples on this also, refraction also they are asking the example. So we'll take example now. Everyone note this example, this is important one. Okay, so given that, everyone concentrate for this example, it is important. Now given that this E1 bar is equal to 2a bar x minus 3a bar y and plus 5a bar z volts per meter. Okay, volts per meter at the free dielectric interface as shown in figure, and d2 bar and the angle theta 1 and theta 2. Okay, so these all are given in figure here. E1 bar is given, E1 bar in medium 1. So this is having relative permittivity of 2. Okay, and this E2 bar is having relative permittivity. For medium 2, the relative permittivity is epsilon R2 here, that is equal to 5. Now in medium 2, the electric field intensity component is E2 bar. okay, and they are making some angles. This E2 bar is making an angle of theta 2, and this E1 bar is making an angle of theta 1 here. Okay, so here what we have to find D2 bar and the angle theta 1 and theta 2. So can anyone tell me how to find this D2 bar? How we can relate this? How we can relate this and how to find this D2 bar and theta 1 and theta 2? Yes, anyone? Okay. So concentrate for this example. This is very important example. Now, here, actually we have to find here D2 bar. Now, this D2 bar is having two components. One is the normal component and another is the tangential component, right? So we can write this D2 bar as D tan 2 plus D n2, right? Now, so we have to find both components of this. So how to find this? We'll see one by one here. So as shown, the z-axis is normal to the surface. So the part of E1 bar is in direction of the A bar. Z is normal component, right? So here what is given? E1 bar is given, and this E1 bar is having two components. That is, one is the normal component and second is the tangential component, right? So here this normal component, that is the perpendicular component, is nothing but your z-axis. Okay, it is nothing but your z-axis, means it is in A bar z direction. Okay, normal component is in A bar z direction. Therefore, for E bar n1, okay, its normal component can be given as E bar n1 is equal to 5 A bar z. Now, how this is taken? Here the total E1 bar is given, that is electric field intensity in all the directions, right? In all directions. So in A bar x direction, A bar y direction, and in A bar z direction. So when we are considering only A bar z direction, this E1 bar will have only the 5 A bar z. Okay, it will have only 5 A bar z. Okay. Now we have to find the total E1 bar. Okay, we have to find here total E1 bar, and this total E1 bar is equal to En1 plus E means E bar N1 plus E bar tan 1. So this E bar tan 1 is equal to E1 bar minus E bar N1. Okay, so simply here it is taken to the left side. Okay, so we are having this normal component, we are having the total component of this E1 bar, that is in dielectric medium 1. So E1 bar is equal to 2 A bar x minus 3 A bar y plus 5 A bar z. This is already given in the question, and minus this En1 bar. So this normal component is in z direction, therefore it is 5 A bar z. Okay, so this is minus En1, therefore it is minus 5 A bar z. Okay, so this 5 A bar z and 5 A bar z get cancelled here, and you are getting it is equal to, means the tangential component of E bar is equal to 2 A bar x minus 3 A bar y holes per meter. Okay, now at the boundary of perfect dielectrics, this E tan 1 is equal to E tan 2, right? We have seen for the perfect dielectrics, two perfect dielectrics when we are considering the two mediums having the permittivity is epsilon 1 and epsilon 2. So for them, the tangential components of E bar are same, right? And the normal components of D bar are same here. So the tangential component of E bar is equal to tangential component of E2 is equal to, now both are equal to 2 a bar x minus 3 a bar y, and it is in holes per meter. Okay, it is in holes per meter, and this is already written here. Okay, now similarly you have to find the d bar component, that is the tangential component of d bar. So this d bar tan 2, this is related by this d bar tan 2 is equal to epsilon 2 into e bar tan 2, because we know that the relationship here, uh, that is d bar is equal to epsilon e bar. Therefore, d bar tan 2 is equal to epsilon 2 into e bar tan 2. So it is equal to epsilon 2 can be written as epsilon 0 into epsilon r2. Okay, epsilon 0 into epsilon r2. And next is e bar tan 2 will remain as it is. And this dn1 is equal to epsilon 1 e bar n1. Okay, so here first we are finding the tangential components and then normal components. Okay, so this d bar n1 is equal to epsilon 1 into e bar n1, and it is equal to epsilon 0 into epsilon r1 into e bar n1. So so e bar n1 is the normal component. Okay, e bar n1 is the normal component. Therefore, this d bar n2 is equal to d bar n1 from the boundary conditions only. We are finding here this d bar n1 uh, uh, because here, hello. So we are finding here d bar n1 from the given data, that is epsilon 1, d bar n1 is equal to epsilon 1 into e bar n1, and it is equal to epsilon 0 epsilon r1 into e bar n1. So formula is there. Therefore, we can find the relation, that is d bar n2 is equal to d bar n1 is equal to epsilon 0 epsilon r1 into e bar n1. Okay, e bar n1. Now we have to find the d2 bar, the total component, the total component. Now, what is there? The total d2 bar is having the two components, that is the tangential component and normal component, right? So as I told you, so this dn1 is equal to dn2, and for the tangential components, there is a relation between this d bar and e bar, as there is a relation between this d bar and e bar with this relative permittivity, right? Means both are related with the relative permittivity. Therefore, this d2 bar is equal to dn2 bar plus d bar tan 2. Means this is for the second region or the second dielectric material only. Okay, so it is equal to epsilon 0 epsilon r1, uh, which is d bar n2. Here you can see that here d bar n1 is equal to d bar n2, right? And we find here d bar n1. D bar n1 is equal to epsilon 0 epsilon r1 into e bar n1, and this is equal to d bar n2. This is equal to d bar n2 only. Therefore, we just put this value there. Okay, that is d bar n2 is equal to epsilon 0 epsilon r1 into e bar n1 plus this d bar tan 2 tangential component we have seen, it is plus epsilon 0 epsilon r2 into e bar tan 2. Okay, so we are taking here epsilon 0 common, into bracket 2 into 5 a bar z. Okay, 5a bar z, which we already obtained there. Okay. So this epsilon 0 into bracket 2 into 5a bar z. Epsilon 0 is taken common here. Epsilon r1, that is the relative permittivity of medium 1 is given here. Here, the relative permittivity of medium 1 is 2 and relative permittivity of medium 2 is 5. Right? Of medium 2 is 5. Therefore, this is epsilon 0 into bracket epsilon r1 is 2 into e bar n1. E bar n1 is 5 a bar z plus this epsilon 0 is common now, and epsilon r2 means relative permittivity of the dielectric medium 2 is 5 into e bar tan 2. Tangential component is 2 a bar x minus 3 a bar y here. So just to put all the values here, epsilon 0 that is 8.854 into 10 raised to minus 12 into bracket 10 a bar z plus 10 a bar x and minus 15 a bar y. Okay, so we are getting this, and again if you multiply in the bracket, we are getting the value in picocoulombs. Okay, because 10 raised to minus 12 is picocoulombs there. Okay, is picocoulombs. So as this dn1 and en1 in same direction. Okay, these are the normal components, and this dn1 and en1 are in same direction, and d1 and e1 are in same direction. Okay, means the normal components are also in the same direction, and only this d1 and e1 are also in the same direction. Therefore, this from that figure only we can write this dn1 and en1 components. That is, first find this cos theta, then you can understand this how to find. So what is this cos theta 1? This is your normal component, right? This is your normal component. This z-axis is also your normal component. So this cos theta 1 is the is nothing but this axis, that is the tangential component, right? Tangential component divided by this E1 bar there, right? E1 bar there. So we'll write there. Okay. So this is for the cos theta 1. Cos theta 1 is equal to, okay, we'll see for the normal component. Okay. So this cos theta 1 is equal to, I think angle will be here, that cos theta 1 is equal to the adjacent side, that is the normal component will be there, that is dn1 divide en1 divided by this e1 bar. Okay, e1 bar. You can consider here both components, that is e bar also and the d bar also. Okay, so when we are finding this d bar component, dn1 is equal to d1 into cos theta 1 dash. Okay, cos theta 1 dash here we are finding. Okay, that's why the normal component is taken, And if this is only cos theta, then there will be the tangential component. So here that theta dash is considered, so that angle is different. That is okay, that angle is different, which is taken to the adjacent side, that is the normal component. Okay, so the normal component dn1 is equal to d1 into cos theta 1 dash. Okay, uh, similarly we can write the component of e bar also. So this en1 is equal to e1 into cos of theta dash 1. Okay, so both components we are writing in terms of your angles. Okay, so theta 1 dash is the angle measured with respect to the normal. Okay, normal component. Then we are having the magnitude, that is mod of e bar n1 is equal to 5. Now why it is 5? This normal component is in z direction. Okay, is in the z direction. So this e bar n1 is equal to, see here, this is this is e bar n1 and it is equal to 5 a bar z. It is in z direction. So the mod of e bar n1 is equal to mod of e bar n1 is equal to 5 and mod of e1 bar, that is the first equation given in example. So it is 2a bar x minus 3a bar y and plus 5a bar z. So for finding its mod, we are taking the square root. So it is square root of 2 square plus minus 3 square and plus 5 square. So it is equal to 6.1644. Okay. Now to find this cos theta I, this cos theta I dash, cos theta 1 dash is equal to en1 divided by e1, and it is equal to, the normal component is 5. Okay, 5 and divided by the total electric field intensity, that is E1 component. This E1 is equal to 6.1644 and it is equal to, totally this cos theta 1 dash is equal to 0.811 and theta dash, that angle is only found, that is 35.795 degree. So that angle is us, and from that only we can find the theta, which is equal to 90 minus theta 1 dash. Okay, so it is 90 minus 35.795, that is 54.205 degrees. So similarly we can find this theta 2 dash. So how this theta 1 dash is taken? It is taken from the given data only here. You can see this angle is theta 1, right? Now the total angle here is 90 degree. So theta 1 dash is taken. So this is your theta 1 dash. Here from Z to E1 bar, your theta 1 dash angle is there. And now we are finding this theta 1, which is 90 minus this theta 1 dash. Okay. So when we are considering, why we are considering this theta 1 dash for the calculation? Because there is normal component only present. Okay, that's why. Okay, so if this theta 2 dash is the angle made by this E2 bar with the normal, then now after that in medium 2 there is theta 2 dash, right? Angle is theta 2 and we have to find the cos theta 2 dash, which is equal to En2 divided by E2 and this En2 2 is equal to okay. Hello. So here we are finding the angle, right? We are finding the angle here. Cos theta 2 is equal to En2 divided by E2, right? Uh, and it is equal to dn2 divided by d2 is equal to dn1 divided by d2. So here this en2 is equal to epsilon 0 epsilon r1 into mod of epsilon mod of e bar n1 and divided by mod of d2 bar we are taking for finding this cos theta 2 here. Okay. So here I'll show that figure. So here this is theta 2 is given. Theta 2 is given. Now theta 2 dash. 2 dash means this is your remaining angle. You have to find there. Okay, remaining angle you have to find. So is anyone in class present? I think the last angle you are not getting. Right. Okay, I'll explain that in next lecture. Okay, any doubt in these boundary conditions? Hello? Any doubts in these boundary conditions? Hello? Anyone having any doubt in boundary conditions? Preeti? समजलंय का? आरती? Okay. So here first you have to understand what are the boundary conditions. Okay. And then uh, you just see if they are asking you any example. Okay. So if they are asking you any example, that time what you have to do, you have to first uh, understand what is the given data, and from that only you can use that formula. Okay, means for example just we have seen that for the tangent that for the boundary E tan 1 is equal to E tan 2, right? Means tangential components of electric field intensity are same and the normal components of electric flux density are same, right? So from these two components, you can find uh, their means if the normal components of the electric flux density are given, from that you can find the normal components of electric field intensity. And if the tangential components of electric field intensity are given, from then you can find the normal components of electric flux density. Okay, so likewise, now you have to first remember what we can find from the boundary conditions, and by using relation d bar is equal to epsilon e bar, we can find the another quantities also. Okay, so we'll see the remaining part in next lecture. So thank you all. So hello, ma'am. I'll make you host.